Welcome to the deep dive. Today, we're plunging into, one of the most fascinating and, frankly, sometimes frustrating paradoxes in the world of large language models, or LLMs. I mean, you've got these AI powerhouses, right? They can write like Shakespeare, debate philosophy, even debug code sometimes.
Yeah, astonishingly fluent.
Exactly. But then you put that same AI in front of a multi-step logic puzzle, something that needs real reasoning, and it often just trips up, gets lost.
It really does. It's like having this brilliant poet who can't solve a simple Sudoku, as you said. It's quite the contrast.
It is. And this fundamental roadblock, it's kind of baffled researchers, hasn't it? It felt like we were hitting the ceiling for AI's actual reasoning abilities.
For a while, yeah.
Yeah.
Until perhaps now.
Okay, let's unpack this then. We're here today to get into a really groundbreaking theoretical paper. It's titled Reasoning by Superposition, a theoretical perspective on chain of continuous thought.
It sounds complex, but the core idea is pretty revolutionary.
Right, this isn't just some small tweak. It feels like it could be unveiling a powerful, maybe entirely new way for these LLMs to actually think, to fundamentally change how they approach complex problems.
Exactly.
So our mission today is to decode this. What exactly is this chain of continuous thought? How does it, transform how LLMs process information inside in that latent space?
And why is it such a big leap forward? Especially for those tricky multi-step problems that LLMs have always struggled with.
Yeah, precisely. Get ready. This could be a bit mind-bending.
It's definitely an exciting deep dive because, this paper, it isn't just throwing out an idea. It actually brings rigorous theoretical proofs and really compelling empirical evidence.
Right. Both sides.
Yeah, it suggests a paradigm shift in how LLMs reason. It hints at a future where these models could tackle much more intricate problems than we thought possible, really pushing the boundaries of AI cognition.
Okay, so let's set the stage a bit first. LLMs, they have shown remarkable performance, haven't they, across a huge range of applications?
Absolutely. Yeah. Content generation, code, you name it.
And a big part of that success, especially when you get into more structured problems, has been these chain of thought techniques. COTI, you've probably seen it, right? Where the LLM doesn't just give you the answer, it first spits out these thinking tokens. It shows its work, basically.
Like showing the steps in a math problem.
Exactly, like a student writing out the intermediate steps. And that's been really effective for things like those tough math competition problems.
That's right. COTI was a genuine game changer. It let LLMs sort of decompose problems, approach them more systematically.
Say there's a limit.
There is. Despite these advances, there's a clear ceiling. LLMs still consistently struggle with tasks that require more sophisticated reasoning capability.
What kind of tasks are we talking about mainly?
We're talking about reasoning and planning problems of increasing scales. Where the number of steps just grows, the dependencies get really complex. And the existing discrete COTI methods, where each thought is like a separate, distinct token, they just hit a wall. It's still an open problem how to expand those methods for the really complex stuff.
The stuff that needs deeper logic, more dynamic searching, maybe?
Precisely.
So to really get at this limitation, the paper uses this great representative problem, directed graph reachability.
Sounds technical, but it's actually pretty intuitive.
Yeah, think of it like a map, right? Cities connected by strictly one-way roads. You start in one city, and the question is simple. Can you actually reach a specific destination city just by following those one-way roads?
It's a classic search problem, yeah.
But why is this such a good test case?
Well, it's a fundamental graph reasoning problem for a reason. It's not just abstract. It actually includes many practical applications as special cases.
Like what?
Think about navigating huge knowledge graphs, like AI systems do, or finding routes in supply chains. Even on a theoretical level, it connects to things like the Turing machine halting problem.
Wow, okay, so it's foundational.
Exactly. Simple premise, but it captures the essence of many real-world reasoning challenges. How AI understands and moves through complex information structures.
So if our current LLMs, even the ones using chain of thought, are hitting this ceiling on problems needing this kind of maybe parallel exploration, what's the way forward? That's been the big puzzle, right?
That's been the puzzle, and that's precisely the radical shift Hal and colleagues propose with chain of continuous thought, or COCONUT.
COCONUT, okay.
It's about moving beyond those discrete, sort of rigid steps, those beads on a string, and embracing something much more fluid.
How so?
The core idea is using continuous latent thoughts for reasoning. not separate tokens. Imagine it less like steps on a ladder and more like a smooth, evolving gradient, a continuous internal state that holds more nuanced info.
Okay, continuous thoughts. And does it work? What are the results like?
Well, that's what's compelling right from the get-go. This isn't just theory, it's showing real gains. Coconut has shown a clear empirical performance boost on synthetic tasks, like that graph reachability problem we just talked about. And also strong performance on real-world math reasoning benchmarks, like GSM-8K.
So it works on both the abstract test case and the practical math problems. That's a good sign.
It's a huge signal. And what's really fascinating is where it truly diverges from traditional COT.
Go on.
The core hypothesis is that this continuous latent thought can actually store multiple candidate search frontiers simultaneously before it even gets to the final answer.
Oh, multiple frontiers. What does that mean?
The paper likens it to a superposition state, drawing that analogy to quantum mechanics.
Ah, like a quantum particle existing in multiple states at once until you measure it.
Exactly. That's the idea they're borrowing.
Okay, let's really unpack that superposition state idea. That sounds like the absolute secret sauce here. How does this continuous state holding multiple possibilities actually give it an advantage?
Well, that analogy is key. Think about traditional discrete COTT. Each discrete thought token, each step, has to be sampled or realized one after the other, sequentially.
Break a path, go down it.
Yeah. The model has to choose a single path sampled from the superposition state at each step. It's like trying to navigate a maze by picking one corridor, seeing if it works, if not, backtracking, trying another. That's sequential search.
Which can be slow and get stuck, right?
Exactly. It requires many more steps and may be trapped into local solutions, like a greedy search, or maybe depth-first search with backtracking.
Okay. So how is continuous thought different?
With continuous thought and this superposition idea, the LLM isn't forced to commit to just one path right away. It's like it can simultaneously exist on all the potential next steps from its current position, exploring them in parallel.
Ah, I see.
Before it has to collapse that state into a single answer later on. This inherently allows for a much more efficient parallel breadth-first search, BFS, exploring many paths at the same time.
Wow. Okay. From trial and error to simultaneous exploration, that's a fundamental shift.
It really is. And this leads right into the paper's biggest theoretical punch. They didn't just observe it working better, they mathematically proved why.
What did they prove?
They showed that a two-layer transformer, just two layers, using these continuous thoughts, can solve that graph reachability problem in a number of steps directly tied to the graph's diameter.
The diameter meaning like the longest, shortest path in the graph.
Essentially, yeah. Think of it as the maximum distance or number of steps needed to get between any 2 points in the network. So the model finds the path in time related to the actual depth of the problem, not just the total number of nodes.
And that's the dramatic part, the efficiency gain, isn't it? How does it compare to the old way?
It's huge. For the same problem, the best known result using discrete COT needs something like ON2 steps, where N is the number of nodes.
Okay, N squared.
But the graph diameter, D, is always less than N, often like way smaller for many real-world graphs.
So D versus N squared.
It means continuous COT isn't just faster, it's potentially exponentially faster for lots of graph types. That's a mind-boggling difference in computation needed, like going from days to minutes for the same problem. Precisely. And that efficiency happens because, like we said, each latent thought vector is a superposition of multiple valid search traces. It enables this implicit parallel search on the graph in each autoregressive step.
Instead of picking one road, it looks down all the next possible roads simultaneously.
From all the places it's currently reached, yeah. And what's so compelling here is having that mathematical proof. It's not just, it seems faster. It's, here's mathematically why it's faster. It points to a fundamental difference in information processing.
And here's something really practical that caught my eye. They showed this works with standard stuff, right? The building blocks of today's LLMs.
Yes, that's a crucial detail. It works with widely used positional encodings like sinusoidal and rotary position embedding, ROPE, things that are common in actual models you use.
Which is a huge deal because sometimes these theoretical breakthroughs need totally custom setups that aren't practical.
Exactly. This makes it immediately more applicable. It's not just a curiosity. It suggests a viable path forward.
It bridges that gap between pure theory and, practical engineering.
Beautifully put, yeah.
Okay, so the theory is super compelling. Exponential speedups, parallel search. But does it hold up when you actually train a model? Did they check that?
They did. The paper explicitly states they performed extensive experiments to verify that our theoretical construction aligns well with the empirical solution obtained via training dynamics. They saw it happen in practice.
Phew. Okay. And what did those experiments show?
The results are really striking. Get this. A 2-layer transformer with continuous cotees outperforms a 12-layer one with discrete cotee on graph reachability.
Wait, 2 layers beat 12 layers?
Yep. A model that's 6 times smaller, way less complex, computationally cheaper, gets better results on this reasoning task.
That says everything, doesn't it, about the power of this continuous approach?
Speaks volumes. It's not just a minor edge, it's a massive leap in efficiency for complex reasoning.
So how did they figure out how it was doing this? Did they peek inside the model's brain?
They did some really clever visualization of the latent reasoning process. For instance, looking at layer 1 attention patterns. They saw the model basically instantiated this copying mechanism. It was linking the source and target nodes onto the tokens representing the edges. Like it was internalizing the graph structure and the goal right away.
Okay, so layer 1 sets up the problem map. What about layer 2?
Layer 2 was all about node expansion. This is where each continuous thought, that latent vector, attends to all outgoing edges from nodes that are currently reachable.
So it's looking at all the next possible steps from everywhere it's currently reached.
Exactly. It confirms the model is expanding its search frontier, just like a breadth-first search algorithm would explore all the neighbors before going deeper. It's like an internal simulation of that efficient search.
But the real aha moment, the kind of mic drop, seems to be how they measured the thoughts themselves, right? Using inner products.
Yes. That was brilliant. They calculated the inner product between the continuous thought at step I and each node embedding, basically measuring how similar or close the current thought state was to each location in the graph.
And what did they find?
They found that nodes within IHOPs exhibit markedly higher similarity scores than distant nodes. Which makes sense, right? The thought state reflects where it's exploring.
Sure.
But even more crucially, frontier nodes are noticeably closer to the thought vector than other reachable nodes.
So the nodes that are candidates for the next step are highlighted.
Exactly. It shows the superposition emphasizes the candidate expansion fronts. It's not just holding all reachable nodes equally, it's dynamically focusing on the ones that are the next possibilities, like saying, okay, these are the doors I'm considering opening next.
That's amazing. It's actively managing the search frontier.
And they also noted optimal nodes are even closer. Maybe because the training data showed it the best paths, so it learned to bias towards those.
Okay, this is already impressive, but here's the part that really gets me, that feels almost mind-boggling. The model figured this out on its own.
That's the kicker. The paper emphasizes that this encoding of multiple search frontiers as a superposition state automatically emerges in training continuous codes without explicit supervision to guide the model to explore multiple paths simultaneously.
They didn't program it to do parallel search, it just learned it.
It discovered this incredibly efficient, almost quantum-like strategy naturally, just through the process of learning to solve the task. It's a spontaneous emergence of a sophisticated reasoning ability.
Wow.
This automatic emergence is profound, really. It suggests that if you give LLMs the right architecture, like this capacity for continuous thought, they might just naturally find these highly efficient parallel ways of reasoning.
It's not just about solving one problem better.
No, it's about understanding how intelligence itself might be emerging in these continuous latent spaces. It hints there are powerful computational properties just waiting there in continuous representations.
So let's connect all these dots then. What's the big so what? What are the implications here for the future of LLMs, for AI in general? This sounds potentially transformative.
I think it really could be. This understanding, this method, it could lead to, well, significantly more efficient and powerful LLMs for complex reasoning and planning.
Tackling problems they just couldn't handle before.
Exactly. Think about problems of increasing scale that currently just overwhelm them. Like intricate logistics planning, navigating massive scientific knowledge bases, complex engineering design where you need to explore tons of possibilities. It also gives us a much deeper, more mechanistic peek into how LLMs think in that latent space, which has been such a black box.
Right.
This suggests a path for real breakthroughs in areas like scientific discovery, where exploring vast hypothesis spaces is key.
And what about that exploration priority thing? That seemed really interesting too, even when they only showed it the best path during training.
Right. Even then, the model still assigned elevated weight to non-optimal frontier nodes. It was implicitly doing a broader, breadth-first style expansion before zooming in on the solution.
It wanted to look around first.
Kind of. And they tested this more with Coconut BFS, where they gave it random supervision on the frontier nodes, and it still performed really well.
Which suggests...
It strongly suggests this BFS-like parallel exploration isn't just something it can do, but it might be an inherent robust property of this continuous thought process. It instinctively explores broadly.
That's fascinating. It's learning a strategy, not just answers.
Precisely. It prioritizes exploration before convergence. And the paper points to future work, too, like formally proving the gap between discrete and continuous Coconut.
Quantifying the difference.
Yeah, and understanding more about how this exploration behavior emerges during training. And of course, seeing if these advantages hold up in more general reasoning settings beyond just graphs.
Which leads to that big question, doesn't it? If this parallel search just emerges naturally.
What else? What other sophisticated reasoning strategies might LLMs be developing in those continuous latent spaces that we haven't even realized or figured out how to harness yet?
This deep dive into reasoning by superposition, it really feels like a glimpse into the next wave of AI, doesn't it? AI that can really grapple with complexity.
I think so. The core takeaway is simple, but profound. Letting LLMs reason by superposition through continuous thought enables parallel search. It lets them solve complex problems like graph reachability way more efficiently, more elegantly.
Yeah, it's not just a technical paper, is it? It feels like a fundamental shift in how we even think about AI's internal processes.
We're moving from that sequential step-by-step view to something that allows for this almost quantum-like thought process, holding multiple possibilities at once. It makes you wonder if the continuous nature of our own human thought might be a blueprint.
Right. So here's a final thought for you, the listener, to maybe mull over today. If LLMs can automatically learn to simulate parallel search, this broad exploration, just in their hidden thoughts.
Like this paper shows.
Yeah. What other complex, maybe human-like cognitive abilities, things like intuition, maybe even creativity or subconscious processing, what else might be spontaneously emerging inside those continuous latent spaces as these models keep getting bigger and better?
And how might we intentionally foster those abilities?
Exactly. The future of AI might be far more dynamic, emergent, and, well, surprising than we've previously imagined.